Hello friends, IBM is here with another episode of Learning Physics, and today I would like to take you through capacitance, the concept of capacitors, parallel plate capacitors, and specifically capacitance of parallel plate capacitors, combination of capacitors, and so on and so forth. That's what we want to get confident with at the end of this discussion, at the end of this video. Do not forget to share the video with your classmates or your friends who are learning the same concepts. This is specifically Cambridge, Physics 9702, and this is paper 4. So, the document required for these past paper questions is attached in the link. If you have not yet downloaded, you can download it. You can always just print per chapter so that you can always follow through when the questions are being solved. You can always pause the video and try to use the concepts you have learned in class to try and solve before you now reveal the answer from the video. So without wasting time, I will take you direct to the document. So we can start from where we stopped. Last time we were dealing with alternating current. And I want us to move to capacitance. I'm not sure how long this video will be or how many episodes this will be in capacitance, but I pray that it is just one. Okay, let us start. Two capacitors, P and Q, each of capacitance C are connected in series with the battery, 9.0 and 9.0 volts, as shown here in the figure. So you notice that this capacitor P and T, they are in parallel with each other if the switch is closed. But again, you see that they are in series with the Q. So switch S is used to connect either a third capacitor T, also of capacitance C, or a resistor R in parallel with capacitor P. Switch S is in position X. So switch S is in position X, so the switch is there. So if the switch is in this position here, calculate the combined capacitance in terms of C. So if the switch is in this position, these two capacitors, this T and P, are in parallel, so total capacitance here is going to be twice C. We just add. Now we assume we have one capacitor at the bottom, which is 2C, which is in parallel, in series with the capacitor Q. The combination of P and T will give us one capacitor, which is again in series with the Q. So since capacitors in series are obtained from the reciprocals, the total capacitance is obtained from reciprocals. So we shall say 1 over total capacitance is going to be 1 over C, that is capacitance for Q, plus 1 over 2C, that is total capacitance in parallel here. And the LCM here is going to be 2C. 2C gives us 2 times that, which is 2 plus 1. So this gives us 3 over 2C as the reciprocal. So it means total capacitance C total is going to be, we get again the reciprocal, which will be 2C divided by 3. So total capacitance here, and when you press your calculator, of course, 2 divided by 3 is around 0.67. So I can write my answer as 2 over 3 times C, or I can write 0.67C. That is total capacitance there. Then the potential, calculate the PD across capacitor Q. Explain your working. PD across capacitor Q, explain your working. So there are several ways of doing this. Note that this capacitance, the capacitance in parallel here is twice the capacitance there. And you remember also that capacitance is equal to Q over V, meaning that PD is inversely proportional. The PD is inversely proportional. The PD is inversely proportional. What does that mean? So it means if I consider the PD, because the capacitor in parallel is twice the capacitor in series, If I consider the PD in parallel to be X, the PD in series is going to be twice X after they are identical capacitors. The capacitance is inversely proportional to V. So if I take the PD across the parallel to be X, then the PD in series will be twice X. In other words, the PD of a capacitor in series is twice the PD of a capacitor in parallel with another one, if they are actually two. Okay, that is one way. Another way could be looking at this at the charge. The total charge in the circuit will be the charge also on each of these capacitor plates, and to be total charge also in the parallel combination. Of course, the charge is shared at this junction here. The charge is shared, but still the total remains the same. Because Q is in series with the battery, it receives all the charge. And the same charge goes to this junction where it is split. Part of it goes to T1 to T, and part of it goes to Q. So we can use the concept of same charge. And I think that is the easiest. Using the concept of same charge, so we have the same charge on Q is the same as the charge on the parallel combination. So there is same charge on capacitor Q as on the parallel combination. So the charge on Q will be the same as total charge on the parallel combination. But remember Q is C times V. Remember Q is equal to C times V. Q is C times V. So the charge is the same. We are saying charge on Q is the same as the charge on the parallel combination, and the charge is C times V. So for Q, the charge will be capacitance C times the potential difference. I will call that one V. So we shall say the charge on Q will be C, capacitance is C times PdV. This should be equal to the charge on the parallel combination. For the parallel combination, the capacitance is twice C. The capacitance of the parallel combination is 2C, and the charge, and the potential difference is now, because for Q we have taken potential difference to be V, then for the remaining part, the parallel combination, the potential difference must be 9 minus V, because total should be 9. So we have equated the charge on Q to the charge on the parallel combination. And when you solve this, you will notice that actually C cancels out, and V is going to be equal to 18 minus 2V, which means that V is going to be equal to 6 volts. That is the potential difference, and remember V is the PD across Q. So that means the potential difference across Q is going to be 6 volts, 6 or 6.0 volts. Alternatively, we can use, because all the charge arrives on Q, we can use the concept of total charge. So total charge, I'll call it Q total, is going to be equal to, from charge is C times V, is going to be total capacitance times total PD, or total voltage supply. Total charge is going to be total capacitance, we got it as 2 over 3C, times PD, which is 9. Total capacitance is going to be 6 times C in columns. Total charge is 6 times C in columns. That is total charge. Remember, all this charge arrives on capacitor Q. Therefore, if I want to find the PD across Q, so I will just say that PD is equal, from this formula here, from PD equals to that, the PD is going to be Q over C, which is going to be total charge 6C, because all the charge appears on Q, divided by C, which still gives you 6 volts. So you can use total charge because it is in series with the battery, it receives all the charge. Alternatively, you can think of the fact that, like I said, the PD across the series combination is twice the PD across the parallel combination. the PD across series combination is twice. This was the second alternative. I'm also saying the PD across the series combination is twice the PD across the parallel combination because capacitance is inversely proportional to PD. If capacitance is twice, then it means PD is a half. So therefore we can say if the PD across the parallel combination is X, then the PD across the series combination will be X 2X. So we say X plus 2X should give us a total of 9. So that means X is going to be a 9 over 3, which is 3 volts. That is for the parallel. Then that means the PD across Q is going to be 9 minus 3, which is still 6 volts. So whichever method is easier for you, you can always use it. Okay, number next. Switch S is now moved to position Y. State what happens to the potential difference across capacitor P and across capacitor Q. So the switch is moved to Y, to the position Y. When the switch is moved to position Y, it means capacitor T is left out. Capacitor T is left out. And therefore, what happens to the PD? If capacitor T is left out, it means actually the PD across capacitor P is going to be actually decreased. It is actually going, because remember when the PD across these two is 3 volts, because if across this one is 6 volts, then across the parallel combination is 9 minus 6, which is 3 volts. It is the PD across P and at the same time the PD across T. But then when the switch is taken to position Y, first of all, P is at 3 volts. P is at 3 volts. When the switch is taken position Y, T is left out, but in position Y, the capacitor must discharge into the resistor. It is going to give its energy to the resistor. Therefore, the PD across the capacitor must gradually decrease from 3 volts to 0 when it fully discharges. So we are saying the PD will decrease. The PD will decrease. The PD will decrease from 3.0 volts to 0. The PD will decrease from 3.0 volt to 0 as the capacitor P, or as P discharges into the resistor. As P discharges into, as the capacitor P discharges into the resistor. Then what happens to capacitor Q? Note that capacitor P is discharging, its speed is decreasing from 3 to 0. And note that capacitor Q was at a PD 6 volts. So when when T is out and P is discharging, its speed is decreasing, the PD across Q must be increasing so that it becomes 9 volts when the PD across 3 becomes 0. Therefore, for capacitor Q, we are saying that as PD across P decreases, the PD across Q increases. Because they're in series, the PD across Q increases, and this will increase from 6.0 volts to 9.0 volts back to the voltage supply. When the PD across P becomes 0, then all the PD supplied by the battery will be across Q. As simple as that. Okay. A capacitor consists of two parallel metal plates separated by an insulator as shown in the figure. Suggest why when the capacitor is connected across the terminals of a battery, the capacitor stores energy. It is energy but not charge. Why does the capacitor store energy but not charge? First of all, we know that the two parallel plates, one has a positive charge, another has a negative charge. And these charges are equal in magnitude, but simply opposite in signs. Therefore, it means total charge of a capacitor is always zero because the opposite plates or adjacent plates have opposite charges. So we can say a capacitor has equal and opposite charges on the plates. A capacitor has equal and opposite charges on the plates. Equal and opposite charges on the plates. What does that mean? So the total charge is zero. So the total charge is zero. But the charging process, remember, involves separating positive and negative charges in the capacitor plates. That means work must be done to separate a positive charge from a negative charge, and the work done is what is stored in the capacitors as energy. So the charging process, the charging process of a capacitor involves separating positive and negative, charges, and the work done to separate the charges is the energy stored. Is the energy stored by the capacitor, or is the energy stored? The work done in separating the charges in the capacitor plates is the energy stored by the capacitor. So we say the capacitor does not store a charge, but it stores energy. The energy stored is equivalent to the work done in separating the charges, the positive and negative charges in the capacitor plates, or on the capacitor plates. Define the capacitance of a capacitor. Since this is just a capacitance, we can simply say it is the ratio of, but they gave us a parallel plate capacitor, so we can actually define the capacitance using these two parallel plate capacitor, and we say this is the ratio of charge on one capacitor plate to the potential difference. To the potential difference. To the potential difference between the plates of the capacitor. So that is capacitance. Ratio of charge on one of the capacitor plates to the potential difference between the plates of the capacitor. The capacitor is charged so that the potential difference between its plates is V0. So it is charged so that the PD between its plates is V0. The capacitor is then connected across a resistor for a short time. It is then disconnected. The energy stored in the capacitor is reduced to 1/6 of its initial value. The energy stored now becomes 1/6 of its initial value. Determine in terms of V0 the potential difference across the capacitor. Determine in terms of V0 the potential difference across the capacitor. So we know that the energy stored by a capacitor, is a half CV squared. So if the capacitor is initially charged to a value of V naught, that means the initial amount of energy, I'll call it E naught, is actually a half C V naught squared. Then the energy stored in the capacitor is reduced to 1/16 of its initial value. So the energy stored in the capacitor later on, I'll call this one E1 now, it is reduced to 2. So the energy after some time, after discharge, becomes 1/16 of E naught. That is 1/16 times a half C V naught squared. So we want to determine, in terms of V naught, the potential difference across the capacitor. So the energy stored after some time is a half, 1/16 of that. But this energy can also be a half times C times the new potential difference V squared. So we are going to just equate these two equations here. Therefore, I will simply say a half C V squared is the same as 1/16 of the energy stored, the first amount of energy, which is a half C V naught squared. And a half C has cancelled. So I'll cancel out a half, I'll cancel out C. And I notice that V squared is going to be equal to V naught squared over 16. When I find the square root, V is going to be equal to 1/4 times V naught. So the answer here is going to be a quarter of V naught. So that is a quarter of V naught. Define capacitance. So this is simply ratio of charge to potential difference. That is capacitance, ratio of charge to potential difference, or you can say charge per unit PD. Charge per unit potential difference, that is capacitance. Charge per unit potential difference, or the ratio of charge to potential difference. That is general capacitance, not necessarily a parallel plate capacitance or capacitance of a parallel plate capacitor. Use the expression for the electric potential due to a point charge to show that an isolated metal sphere of diameter 25 centimeters has a capacitance of 1.4 times 10 power negative 11 farads. Okay, so we want to use the expression. Use the expression for the electric potential due to a point charge to show that an isolated metal sphere of diameter 25 has a capacitance of that. So from electric fields, we know that electric potential V is equal to charge over 4 pi epsilon naught times R. And we now know from capacitance that capacitance is equal to Q over V. So when we combine the two for a sphere, then the capacitance C is going to be Q divided by Q over 4 pi epsilon naught R, which is going to give us 4 pi epsilon naught times the radius. Now we substitute, so this will become 4 pi. Epsilon is permittivity of free space, which is 8.85 times 10 power negative 12. And R is, they gave us the diameter as 25, so R is going to be 12.5 times 10 power negative 2. This is the radius. So press our calculator. 4 pi times 8.85 exponent negative 12 times 12.5 exponent negative 2. So this is giving me 1.39 1.39 times 10 power negative 11 farads, or approximately 1.4 times 10 power negative 11 farads. So that is the capacitance as required. Three capacitors of capacitance are 2.0 microfarads, 3 and 4 are connected as shown here. Determine the combined capacitance of three capacitors. So these two are in, this one and this one are in parallel, we just add them to get 6 microfarads. Then the 6 microfarads is in series with 3, so we can use product over sum, or you can just say 1 over total capacitance is equal to 1 over 3 0.0 plus 1 over 6.0, or you notice that total capacitance will be the product over the sum. Since they are 2, 6.0 times 3.0 over 6.0 plus 3.0. This is 18 over 9.0, which gives you 2.0 microfarads. Determine the potential difference across the capacitor of capacitance 3 microfarads. So I want you to note again that the capacitor of capacitance 3 microfarads is in series with the battery, so it receives all the charge. So we can find its PD by using total charge and total capacitance. That's number one. Number two, we also know that total charge on the capacitor of 3 microfarads is the same as total charge in the parallel combination. But for the parallel combination, total capacitance is 6 microfarads. So the charge is the same. The charge is the same. So if we use the simplest is to use same charge. Since charge is the same, and yet we know that charge is equal to V times C, or C times V. For 3 microfarads, I'll say the PD across this one, let it be V. And then the PD across the parallel combination will be 9.0 minus V. But remember, charge is the same. Total charge for 3 microfarads is the same as total charge for the 6 microfarads. So we just equate. So for the 3 microfarads, charge will be capacitance, which is 3.0 microfarads times the PD, which is V. This should be equal to the 6 microfarad capacitance, then times the PD, which is 9 minus V. We solve for V, and when you try to solve for V, you have that 3V is equal to 36 minus 6V, which means that V is it 36? 9 times 6, that is 54, not 36. So this is 54. So you have that 9V is equal to 54, which implies that V is 54 divided by 9, which implies that V is equal to 6 volts. So it means the PD across 3 microfarads is 6 volts. I've considered the same charge on both the series and the parallel combination. I can now also consider total charge. So total charge, this is another alternative. Total charge in the circuit. Total charge is going to be total capacitance by the total charge is the same as the charge on the 3.0 microfarad capacitor, because it is in series with the battery, and total charge is equal to total capacitance times total PD. Total capacitance, we have calculated it as 2.0 above. Total PD is 9, meaning total capacitance is 18 microfarads. So the PD across the charge, the PD is going to be charge divided by the capacitance. Now we are looking at total charge because it is the same as the charge on the 3 microfarad since it is in series. But then for capacitance, we shall consider the 3 microfarad capacitance. So this is going to be total charge, which is 18. By the way, total charge is not in microfarads; it is in microcoulombs. This is in microcoulombs, so this is 18 microcoulombs divided by 3 microfarads. So this gives us 6 volts because micro cancels coulombs over farads, that is going to be volts. So we could also use that. Alternatively, you notice that 3 is a half of 6 volts, 6 microfarads. That means the PD across 3 microfarads is going to be twice the PD across 6 microfarads. If we say that the PD across the parallel combination is X, then the PD across 3 microfarads is going to be 2X, because PD is inversely from capacitance is equal to Q over V. PD is inversely proportional to the capacitance. Where the capacitance is twice, the PD is a half. So we could still say X plus 2X is equal to 9.0 volts. That means X is going to be 9 over 3, which is 3 volts. That is the PD across the parallel combination, which means that the PD across 3 microfarads is 2X, so it will be 2 times 3, which is again 6 volts. So whatever method is easier for you, you can always use it. So we have got here the answer as 6.0 volts. Okay, so next, determine the positive charge stored on the capacitor of capacitance 2 microfarads. Determine the positive charge. So we now know that the PD across the parallel combination will now be 9 minus 6.0. So PD is going to be 9 minus 6, which gives us 3.0 volts, which gives us 3.0 volts. Then the charge, which is we are interested in, the charge is going to be C times V from the formula. Then the capacitance is 2 microfarads, so that will be 2.0 times the PD, which is 3 volts. Now remember, this is in microfarads, the other one is in volts. So the answer you're getting here is 6.0 microcoulombs. So this is 6.0 microcoulombs. It is micro because I didn't change the capacitance from microfarads. Okay. The rectified output of a sinusoidal signal is connected across a resistor R of 1.5 kilo, that is kilo ohms, 1.5 kilo, that is kilo ohms, as shown in the figure there. The variation with the time t of the potential difference V across R is also shown in the figure. So here we have variation. You notice that the peak is, I think this is 6. The peak is at 6. State how the rectification shown in the figure may be achieved. You notice that the rectification in the figure here is a half wave. We have half of the cycle is missing. Then we have one positive half of a cycle. So it is half wave rectification. And how do we achieve half wave rectification? We said you connect a diode in series with either the load. So we connect a diode in series with the source or with the load. We connect the diode in series with the source or with the load. So state how the rectification shown may be achieved. How is half wave rectification achieved? So we are saying connect a single diode. Connect a single diode in series with the load R, or in series, or it can be in series with the AC supply. It can be in series with the AC supply. Okay. A capacitor is now connected, so you must ensure that you connect a single diode in series with the AC supply or with the load to achieve a half wave rectification. The capacitor is now connected in parallel with the resistor R. The resulting variation with time t of the potential difference V across R is shown here. So here we have a capacitor. Of course, we know that a capacitor reduces fluctuations. It prevents the output voltage from going back to zero. Use the figure to determine the mean potential difference across the resistor R. We want the average potential difference. So the maximum is 6.0 from the graph. This is 6.0, and this is, I think, at 4.8. That is 4.8. So the average is going to be 6.0 plus 4.8 divided by 2. And I think this gives us 5.4. So that is 5.4 volts. Then the mean current, the average current. So the average current is going to be called the average voltage is going to be called the average current times the resistance. So the mean current is going to be the average value of PD, which is 5.4, divided by the resistance, which is 1.5 kilo ohms, times 10 power 3. I press my calculator. From the calculator, this is 3.6 times 10 power negative 3. The time in each cycle during which the capacitor discharges through the resistor. Where does the capacitor start discharging? So if I consider this part of the cycle here, this part here, the capacitor is charging, and here the capacitor is discharging. So the capacitor, let's say it starts discharging from 0.03, and it is stopping discharging at this point here, which I think it is 1, 2, 3, 4, 5, 6, 7. 7 times, so that is 0.057, I guess. So we get the time interval between 0.03 and 0.057. That is 0.057 minus 0.03, and that is 0.027. So the time for discharge is 0.027 seconds. Using your answer in Roman 1, calculate the charge passing through the resistor during one discharge of the capacitor. So we know that charge is current times time. The current, we have calculated it as 3.6 times 10 power negative 3. The discharge time we have seen from the graph is 0.027. When I press my calculator, so from the calculator I am getting the charge as being 9.72 times 10 power negative 5. The capacitor, okay, using your answer again, Roman 1, we want to find to calculate the capacitance of the capacitor. So the capacitance is going to be simply now the charge over the difference in the PD during discharge. So the charge which is passing through the resistor during one discharge is 9.72 times 10 power negative 5. Then the difference in PD. From the graph, the difference in PD is during discharge is 6.0 minus 4.8, which is 1.2. So the difference in PD, delta V, is going to be 6.0 minus 4.8, which is 1.2. So here we shall put here 1.2 volts as delta V. So when I press the calculator, simply divide. When I divide by 1.2, it is giving me 8.1 times 10 power negative 5. 8.1 times 10 power negative 5. The second capacitor is now connected in parallel with the resistor R and the first capacitor. So in other words, there are two capacitors that are in parallel. When we connect capacitors in parallel, total capacitance is increased. Okay, so we have a higher capacitance. Draw a line to show the variation with the time t of the potential difference V across the resistor. Now that the capacitance has been increased, your teacher must have told you, or you must have not mentioned in class, that the smoothing it depends on the product R times C. A large value of C makes the product RC larger, so it means the capacitor discharges very slowly. A large capacitor discharges very slowly. This means the voltage is maintained to a higher value for a long period of time. Therefore, they want us to draw a new graph on the same peak, on the same axis, to represent to show the potential, the variation with the potential with the time when another capacitor is added. Adding another capacitor means high capacitance, and the higher the capacitance, the better the smoothing, or the higher the smoothing. Therefore, our fluctuations, the fluctuations of the graph will not reach the same value as before. If it reached 4.8 today, this time when we have another capacitor in parallel, we have increased the capacitance, it will not reach there. Let's say it reaches at maybe this point here. So I'll make it reach at this point here. Okay, so just show this part of charging, and of course the discharging part. Okay, so this is now going to be our new curve, our new graph. It is more of, there is less fluctuation. The graph is not falling further down as it used before, as it did before. So just use a ruler and draw a very nice graph, not forgetting this part of charging of the capacitor. Okay, so that is our graph. We can move to the next question. Some capacitors are marked 48 microfarads, safe working voltage 25 volts. Show how a number of these capacitors may be connected to provide a capacitor of capacitance 48 microfarads. Safe working voltage is 50 volts. So what is available? The voltage available is 50, but remember the PD across each capacitor should not go beyond 25 volts. And total capacitance is going to be 48 microfarads. So you can't use, they want you to show how a number of these capacitors. So you can, if you say it is one capacitor, because each capacitor is 48, then it means the PD across it will be 50, which is higher than 25. So you have to look for a simple a way of combining this so that the PD across the capacitor is 25, each capacitor is 25, when 50 is supplied, and the total capacitance is 48. One simpler way could be thinking of two capacitors in series in parallel with another pair of two capacitors like this. So these leads show that this is where they connected the 50 volts. If this, you try to check the total capacitance here, you can just try to check if it is 48. Each of these capacitors is 48. So those which are in series, we shall say product over sum for those capacitors in series. So when you press 48 times 48, 48 times 48 divided by 96. So when these ones in series, when you combine them, you get 24. This one is also 24. Now in parallel, you just add them, 24 plus 24, which is 28. So it means that arrangement is correct. Here there is no specific formula. You just check using a simple method. So simple techniques of checking the total capacitance. You also notice that the PD has not been violated because if this is 25 and this is 25, total is 50. Even here, the total will be 50 because the upper section is in parallel with the bottom section. So still the PD across each is 25 and total is 50. Alternatively, you could also come up with this one. So this is another alternative. So how about if you have two in parallel with each other, but again in a series? So in series with another one. So of course the PD across each of these is 25. These are connection leads for the PD. But total capacitance here for these ones in parallel, total capacitance here is 48 plus 48, which is 96. Here it is also 96. Now they're in series, you try to check 96 times 96 over 96 plus 96. And automatically this is giving me 48. That means my combination is correct. So you have to think of a better way of drawing and always also minimize the number of capacitors you add or you join together. You can't use infinitely many, even though they have not put a restriction on how many you should use. Okay, number next we have this should be 72 microfarads. Safe working voltage is 25. Safe working is 25, and therefore you should not go beyond 25 volts across one capacitor, and the total capacitance should be 75. 72. You notice that 72 is the same as 48 plus 24. That means we need to have capacitances giving us 48 so that it is in parallel with another one which is giving us, or with others which are giving us 24. So in other words, we can have one capacitor of 48 in parallel with two capacitors that are in series, because in series they will give us 24. That is, so I will have something like this, one capacitor which is in parallel with the two. So that one gives us 72, because those ones which are in series give us a total of 24, and we add 24 plus 48 which is in parallel, that gives us 72. Okay. Alternatively, you could also have many more than this. You could have, say, because we saw that this was 24. Suppose we add another one again, I think it will have reached 72. So we can have three sets in parallel. Sorry, I missed out one capacitor. So this one also gives us 72 because we have 24, 24, 24, which is 72. So you need to be creative enough when you are coming up with these combinations. For whatever combination, try to check and see if you arrive at total capacitance as required. If yes, then the combination is fine. But many times it is not advisable to use so many capacitors. State what is meant by electric potential at a point. I think we define this in electric fields. The work done in moving a unit positive charge from infinity to the point. The work done in moving a unit positive charge from infinity to the point. So that is electric potential. Define capacitance. This is the ratio of charge to potential difference. The ratio of charge to potential difference, that is capacitance. The variation of the potential difference V of an isolated metal sphere with the charge Q on its surface is shown here. So they have given us a graph which is a straight line, as you can see. Okay, an isolated metal sphere has capacitance. Use the figure to determine the capacitance of the sphere. So from the graph, we can just take a few readings. We can just take some readings. The scale here is, I'll just take between, say, 150. Let me take 150. Okay, 150 is at the center here. That is, the scale is 0.5 divided by 10, which is 0.05. So this is 1, 2, 3, 4. So this is going to be 2.7. That is 2.7. So we are finding the capacitance. I'll just use the formula. Capacitance is equal to charge over V. So the charge is 2.7 times 10 power negative 6 divided by corresponding value of V, which is 150. But on the vertical, we have kilovolts. So that is 150 times 10 power 3. Then I press my calculator. From my calculator, I have 1.8 times 10 power negative 11 farads. The electric potential energy stored on the sphere when charged to a potential of 150 kilovolts. We want electrical potential energy. So energy is a half CV squared, or you could use energy is a half QV. And here you would use Q as C times V. So this is going to be a half times C, which is 1.8 times 10 power negative 11. Then the PD is 150 times 10 power negative power 3. Power 3, 150,000 hertz. Yes. So you press your calculator. And by the way, this is squared. So from my calculator, this is 0.20 to two significant figures. A spark reduces the potential of the sphere from 150 kilovolts to 75 kilovolts. Calculate the energy lost from the sphere. So we want the energy lost in this point here. Remember, energy is equal to a half CV squared. So the change in energy is going to be a half. The capacitance is remaining the same, 1.8 times 10 power negative 11. There's just a change in PD from 150 times 10 power 3, and this is squared, up to 75 times 10 power 3, and this is also squared. We just simply press our calculator. So from my calculator, I arrive at 0.15 joules. Define capacitance. You don't get tired to define capacitance. The ratio of charge to potential difference. charge to potential difference, that is capacitance. An isolated metal sphere has a radius r. When charged to a potential V, the charge on the sphere is Q. Radius r, when charged to potential V, the charge on the sphere is Q. The charge may be considered to act as a point charge at the center of the sphere. State an expression in terms of R and Q for the potential V on the sphere. We saw this in electric fields. So potential is equal to charge over 4 pi epsilon naught R. We saw that in electric field potential. This isolated sphere has capacitance. Use your answer in A to show that the capacitance of the sphere is proportional to its radius. So capacitance is charge over potential, and yet we have seen that potential is again charge over 4 pi epsilon naught R. So this means capacitance is going to be 4 pi epsilon naught times R. So since 4 pi epsilon naught is a constant, so we say that capacitance is directly proportional to the radius. Since 4 pi epsilon naught R is a constant, so we say capacitance is directly proportional to the radius. The sphere in B has a capacitance of 6.8 picofarads and is charged to a potential of 220 volts. Calculate the radius of the sphere. So from the expression, we shall now see that the radius is going to be the capacitance divided by 4 pi epsilon naught. I'm just manipulating that. So we substitute 6.8 times 10 power negative 12 for pico divided by 4 pi times 8.85 times 10 power negative 12. I press my calculator. So from my calculator, this is divided by, from my calculator, I get 6.1 times 10 power negative 2. Calculate the charge in coulombs on the sphere. So we know that charge is capacitance times V. So capacitance is 6.8 times 10 power negative 12. And the potential is 220 volts. The potential is 220 volts. Then when you press your calculator, times 220. So the charge is going to be 1.496 times 10 power negative 9 volts. I mean coulombs. That will be the charge. Okay. The second uncharged metal sphere is brought up to the sphere in C so that they touch. The combined capacitance of the two spheres is 18 picofarads. Combined capacitance. Okay. By the way, this would round off to 1.5 times 10 power negative 19 coulombs. So the combined capacitance is 18 picofarads. Okay, we see that the capacitance has increased. Perhaps they have been combined in parallel. Calculate the potential of the two spheres. So potential of the two spheres will be equal to the charge over capacitance. Note that the second capacitor was not charged, so total charge remains the same as the charge on the first capacitor. So the charge is going to be 1.5 times 10 power negative 19 divided by total capacitance, which is 18 times 10 power negative 12. So total charge is not violated. The total charge of the charged capacitor is what is shared with the second capacitor. So I press my calculator here. So from my calculator, I get this as 83 to two significant figures. Then part 2, the change in the total energy stored on the sphere when they touch. The change in total energy stored on the sphere when they touch. Note that energy of a capacitor stored is half CV squared. So the change in energy, the energy stored before they are put together is going to be a half. Total, the capacitance was 6.8 times 10 power negative 12 times the PD before they were put together, it was 220 volts. Minus, now when they are together, this will be a half. Total capacitance is 18 times 10 power negative 12. And we are seeing that the potential is 83. So this will be times 83 squared. So I press my calculator to get the difference, change in energy. So the change in energy that I'm arriving at here is 1.03 times 10 power negative 7 joules. You could also have used the capacitance, you could also have used the half QV. You could also have used the half QV because the charge remains the same. Okay, state two functions of capacitors in electrical circuits. Functions of capacitors, these are almost 10. I'll state a few. Number one, capacitors are used for blocking DC because many times capacitors have even insulating materials between them. They can block or direct current. We have seen capacitors are used in smoothing, that is, reducing the fluctuation or variation of the output unit direction of voltage from the AC. Number three, capacitors are used for storing energy. Storing energy, for example, the flash unit of a camera. Number four, capacitors are used to produce time delays. Producing time delays. Producing time delays. In other words, they are used in timing. Number four, capacitors are used in tuning circuits, like those of TVs and radios. Next, capacitors are used in coupling. Coupling means joining one circuit to another or linking one circuit to another. Capacitors can be used to join circuits or link circuits. Capacitors also allow separation of charges. They allow separation of charges. Capacitors prevent surge or prevent acing or prevent sparks. They prevent acing or sparks. Of course, capacitors prevent acing or sparks by producing time delay. The charge which would otherwise cause a spark, it can be stored by the capacitor plate and given out gradually. Capacitors are used together with other circuits to produce electrical oscillations. Capacitors are used to produce electrical oscillations. By the way, capacitors can be used as temporary power supply. Temporary power supply. So all these are some of the applications or functions of capacitors. Three capacitors, each marked 3 microfarads, 6 volts maximum, are arranged as shown here. Determine for the arrangement the total capacitance. So each of them is 30 microfarads. So these ones in parallel, we shall add them 30 plus 30, that is 60 microfarads. It is now in series with another 30 microfarads. So since there are only two, we can use product over sum. So in a series, we use reciprocals. 1 over C total is going to be 1 over 30 plus 1 over 60. But this is the same as product over sum. So total is going to be 30 times 60 over 30 plus 60. Press your calculator. Total capacitance is 20 microfarads. Then the maximum potential difference that can safely be applied between points A and B. The maximum potential difference that can be safely be applied between points A and B. Note that A is, they have said the three capacitors each are marked 30 microfarads and 6 volts maximum. Note that the PD in parallel is going to be half the PD in series, because capacitance is inversely proportional to the PD. The PD in parallel is twice the PD in series, so the reverse is very true. So we are saying PD across the parallel combination is half the PD across the parallel combination is equal to a half times the PD across the single capacitor. If the capacitors are in parallel, total capacitance is higher. That means the PD reduces, because from the formula, capacitance is charge over V. If total charge is the same, then capacitance is inversely proportional to PD. So if we say the PD across the single capacitor is what? The PD across a single capacitor is V. Then the PD across a parallel combination is going to be half V. So we shall say half V plus V should give us the total possible PD. And remember, the maximum is 6, so this will be a half times 6 plus 6, which would give us 3 plus 6, so that would be 9.0 volts. So if here there is 6 volts, here it should be 3, so that total is 9 volts. So the maximum potential difference that can safely be applied between points A and B is 9.0 volts. This statement is very important, that the PD across parallel combination is half the PD across a single capacitor. A capacitor of capacitance 4700 microfarads is charged to a potential difference of 18 volts. It is then partially discharged through a resistor. The potential difference is reduced to 12 volts. Capture the energy dissipated in the resistor during the discharge. So the energy is going to be a half CV squared, or you can use a half QV, where Q is CV. But since they have given us V and C, I will use a half CV squared directly. We want the energy which is dissipated is the difference in the energy which was there and the energy which is present after discharge. So the energy dissipated, I will use delta E for energy dissipated to be a half times 4700 times 10 power negative 6 to change from microfarads to farads. Then times difference in PD, that is 18 squared, because V is squared, minus 12 squared. Do not be tempted to say 18 minus 12 and square. Not at all. That's wrong mathematics. This would be wrong mathematics. So I press my calculator. 18 squared minus 12 squared times 4700 exponents negative 6 divided by 2. So I am getting the energy dissipated in the resistor to be 0.42 joules. 0.42 joules. A student sets up the circuit as shown in the figure. Measure the charge on a capacitor C for different values of potential difference across the capacitor. So a student has set up such a beautiful circuit. Okay, we have to measure, some emitter here is to measure the charge The capacitor, the switch can be turned this side or the other side. We have a variable power supply and a voltmeter cross. The variation with potential difference V of the charge Q stored on the capacitor is shown in the figure. So they have showed us here the variation in the figure. So you see that the values have been plotted. The values have been plotted. State and explain how 7 point, the figure indicates that there is a systematic error. Note that a systematic error is going to make values to be either above or below the true value by a constant amount. Let's check if there is a systematic error. If there is a systematic error, the line of best fit will not go through the origin, will not go through 0, 0. So we can try to draw the line of best fit to see if there is a systematic error. If the line does not go to 0, 0, if it is impossible to come up with a line of best fit which goes through 0, 0, then there is a systematic error. I cannot actually draw it here because the points will not be balanced. So the best line of best fit, or the line of best fit, is most likely going to be here. The line of best fit is most likely here. If you are very observant, the line of best fit is most likely there. You can increase the thickness. The line of best fit is somewhere there. I think you can see now the points are almost balanced. The points are almost balanced. In fact, if I was to add just hit this second point, the point at the bottom would be on the line. Okay, so that is my line of best fit. It is not going through the origin, it is actually touching this point here. So there is a zero error because the line of best fit does not go to the origin. So state and explain how the figure indicates that there is a systematic error. So the line has a non-zero intercept, so does not pass through the origin. The line has a non-zero intercept. The line has a non-zero intercept, so it does not pass through, the origin. The line has a non-zero intercept, so it does not pass through the origin. So there is a zero error. Alternatively, if there was no systematic error, charge should be proportional to PD. Alternatively, you could say for no systematic error, for no error, for no systematic error, charge should be a proportional. Charge should be proportional to PD if there is no systematic error. But now it is not proportional because when the charge is zero, there is a PD. When there is a PD, there is no charge, so they are not directly proportional. So there is a systematic error. Okay. In other words, there is a zero error if I'm put like that. Use the figure to determine the capacitance in microfarads of capacitor C. So we want to find the capacitance. So we can find maybe the gradient of best fit. Let's find the gradient of best fit. I think it will be the easiest. I'll consider, let me see, 1, 2, 3, 4, 5. Okay, so I will consider this. This is 12.5 against against 5. 12.5 against 5. And then this one is 0.5. So I will use the gradient because it is charge against V. We know that capacitance is equal to Q over V, so I can find the gradient. So the gradient of the line of best fit the best fit line is going to be 12.5 minus 0 on the vertical divided by 5.0 minus 0.5 on the x. And this is going to be this is so this is going to be 2.78 times 10 power negative 3. But we want the answer in micro. This one is in farads. In micro, it is going to be 2.78 times 10 power negative 3 divided by 10 power negative 6. To change it to micro, we divide by 10 power negative 6. 10 power negative 6. And this would be 2.78 times 10 power negative, what is this, times 10 power 3, positive 3. Okay, 2.76 times 10 power 3. And this is giving me approximately 2,800 microfarads. Those are two significant figures. Or you can write 2,780 microfarads. Use your answer in B to determine the additional energy stored in the capacitor C when the potential difference across it is increased from 6.0 volts to 9.0 volts. So I will use this answer here to determine the additional energy. Okay, so energy, remember, for capacitor is going to be a half CV squared, or you can use a half QV, and you know that Q is CV. You can use that, Q is CV. So the difference in energy is going to be a half times the capacitance is 2,800 times 10 power negative 6. I chose to use that to round off that value. Then times the difference in values of V, which is 9.0 squared minus 6.0 squared. So that we want to find the additional energy when the PD changes from 6 to 9. So that is the difference is the additional energy. So I press my calculator. So this is 6.3 times 10 power negative 2. 6.3 times 10 power negative 2. Oh, again, state two functions, two uses of capacitors in electrical circuits other than smoothing of direct current. Apart from smoothing of direct current, what are other functions of capacitors? So we said number one, capacitors are used to block or DC, to block direct current. Capacitors are used to prevent sparks or to prevent acing. Capacitors are used to produce electrical oscillations. Capacitors are used for storing energy. They are actually temporary. I think temporary is O. Capacitors are temporary power supply. They can be used as temporary power supplies. Capacitors can be used in tuning circuits. Capacitors can be used to produce time delay in timing circuits. Timing. They are used in timing circuits to produce time delays. So the list is long. They can be used in coupling. Remember coupling, I said that is linking one circuit to another circuit. That is coupling. So you can't fail to state only two out of these. There are so many. Blocking DC, preventing S-ing, that is preventing production of sparks, or preventing surge they prevent surge, produce electrical oscillations, storing energy, temporary power supply, tuning circuits of radios and TVs, timing circuits to produce delays. There is what we call coupling, that is linking one circuit to another. Those are uses of capacitors. The combined capacitance between terminals A and B of the arrangement shown in the figure is 4 microfarads. Total capacitance is 4 microfarads. Two capacitors each of capacitance C and the remaining capacitors each having 3 microfarads are shown here. The potential difference between A and B, that is total PD across all the capacitances, is 12 volts. Determine C. So this is an easy question. First of all, these ones are in parallel, which the total is going to be 6 microfarads. These two are in series. The total is going to be C times C over C plus C, which is going to be C squared over 2C, which is C over 2. So now the C over 2 is again in parallel with the 6 microfarads. So we get total capacitance again using reciprocals or product over sum. Or you can say 1 over C total is now going to be 1 over C over 2 plus 1 over 6. That is going to be the total. But remember the total was given as 4.0. So this is going to be 1 over, let me just first get the totals so I equate it to 4.0. So this means 1 over C total is going to be product over sum. That will be 6 times C over 2 divided by 6 plus, sorry, let me just do it mathematically, the way mathematicians, because I know some PCB students may fail to solve this. So this is going to be the same as 2 over C plus 1 over 6. Then you get C total is going to be the product of a sum, that is 6 times 2 over, 6, why is this disturbing me? So we have in the denominator, we have 6 times 6, 6 times C, not 6 times 6. 6 times C divided by, which one is the easiest mathematics now to solve this? Okay. So LCM, 1 over C total is going to be equal to the LCM, which is 6C. So 6C gives us 6 times 2, which is 12, plus 6C gives us C, that is times C. So it means total C total is going to be 6C again over 12 plus C. But remember, total value of C was actually total value of C, or total value of capacitance, C total was 4. So we shall say 6C over 12 plus C is equal to 4.0. I'm doing all this just for non-mathematics students, but for math students, we don't do all this. In fact, we would have got product over sum from here and equated it to 4.0 directly, product over sum. So this means when you cross multiply, you have 6C is equal to 48 plus 4C. And when you take 4 the other side, then it becomes 2C is equal to 48 and C is equal to 24. So total, the value of C is 24 microfarads. For mathematicians, you would just have got it from here directly, product over sum, you get total capacitance and equate to 4.0. What remains is algebra, not physics. It's algebra, not physics. Calculate the magnitude of the total positive charge transferred to the arrangement. Magnitude of the total positive charge. All the positive charge appears on the what? The capacitors in series. All the total charge appears on the capacitors in series. So total charge is going to be total capacitance times total PD. So total capacitance was given as 4.0. Then times, was it microfarads? 4.0 microfarads, that was the total capacitance. So 4.0 microfarads times the PD, which is given as 12. And this gives us 48 microcoulombs because this is volts. So this is going to be 48 microcoulombs. Then use your answer in Roman 2 to state the magnitude of the charge on one plate of a capacitor of capacitance C. Note that all the total charge appears on the capacitors in series. So the answer here is going to be 48. So total charge is on C. Total charge is on C because it is in series with the power supply. Since all the charge in the circuit appears on these capacitors that are in series, but it divides at this point here in the ratio of the resistances. So next part, a capacitor of capacitance 3 microfarads. Because they are identical, charge is divided equally. Alternatively, we can say twice Q is equal to 48, which means Q is equal to 24. So we can say since they are identical, charge divides equally. If they were not identical, the one with the more capacitance would have more charge. So this is going to be 24. Okay, next. Define capacitance, that is the ratio of charge to potential difference. Ratio of charge to potential difference. Ratio of charge to potential difference. That is capacitance, ratio of charge to potential difference. Three capacitors of capacitance C1, C2, and C3 are initially uncharged. They are then connected in series to a battery, as shown here. The battery applies a potential difference V across the three capacitors. Show that the combined capacitance C of the capacitors is given by this expression. So what do we know about capacitors in series? The charge is the same. So we start from that point. Charge is the same. Charge is the same, and we know that the total value V is going to be V1 plus V2 plus V3. The charge is the same. So the charge is the same, and we are going to simply call it Q. Then total PD across all of them is the sum of all the PDs. And we know that PdV is going to be Q over C, because capacitance is charge over V. So V is Q over C. So we now substitute. For V, we shall have Q over C. For V1, since Q is the same, we shall have Q over C1 plus Q over C2 plus Q over C3. So this means we now have that Q over C is equal to Q into 1 over C1 plus 1 over C2 plus 1 over C3. So Q cancels. Therefore, we now know that 1 over C is equal to 1 over C1 plus 1 over C2 plus 1 over C3. As simple as that. What is very important is to note that when capacitors are in series, the charge is the same. Okay. A battery of EMF 12 volts and negligible internal resistance is connected to a network of two capacitors and a resistor as shown here. The capacitors have capacitances of 200 microfarads and 600 microfarads. The switch has two positions, A and B. The switch is moved to position A. When it is moved to position A, when this part is closed here, you notice that 600 and 200 are now in series. We can find total capacitance. So total capacitance will be 1 over C total is equal to 1 over 600 plus 1 over 200. Because there are only two, I will just say product over sum. So C total is going to be the product 600 times 200 over 600 plus 200. Product over the sum. When I press my calculator, 600 times 200 over 600 plus 200. I am getting 150 as total capacitance for the two. Then the charge on the 600 microfarad capacitor. The charge on the 600 microfarad capacitor. Because they're in series, total charge in the circuit goes on each of these plates. So we just look for the total charge. So the total charge Q is going to be equal to total capacitance times total PD. So total charge is going to be total capacitance, which is 150 times 10 power negative 6 times the total PD, which is 12. So this is 1.8 times 10 power negative 3. Because they're in series, all the charge in the circuit goes on each of these plates. Therefore, the charge on the 600 microfarad capacitor is going to be 1.8 times 10 power negative 3 coulombs. Alternatively, you can think about it in terms of the PDs across each. Remember, capacitance is Q over V. The one with the high capacitance has a smaller PD. So, and you notice that 600 is 3 times 200. That means the PD across 200 is 3 times the PD across 600 microfarads. If we say the PD across 600 is X, the PD across 200 is going to be 3X. So that 3X plus X is equal to 12 and X will be equal to 4 volts. That is the PD across 600 and the PD across 200 will be 80 volts. Then if you want to find the charge, still charge will be equal to capacitance, which is 200 times 8. 200 times 8 volts. Is it 8? Sorry, this is 3. So it is 200 times 9. Because if this is 3, 4x, 12 divided by 4x is 3 volts. PD across this is 3 volts. So it means across this one is 9. So charge will be 200 times 9. Remember, this is microfarad. So that is 200 times 10 power negative 6 times 9, which takes you back to the same answer, 1.8 times 10 power negative 3 coulombs. Then the PD across the 600 microfarads. If now we know the charge, find the PD is easy because PD is going to be charge over C. From capacitance equals charge over V, PD is charge over C. The charge on the 600 is 1.8 times 10 power negative 3. The capacitance is 600 times 10 power negative 6. When you press your calculator, this gives us 3.0 volts. The switch is now moved from position A to position B. Let's see what happens to position B. If it is moved from position A to position B, it means the capacitor of 600 microfarads must now discharge. It must now discharge into the load, into the resistor. Okay? Calculate the potential difference across the 600 microfarad capacitor when it has discharged 50% of its initial energy. Let's find its initial energy. Its initial energy, the energy is going to be a half CV squared. Its initial energy is going to depend on its initial PD before it is turned to position B. So initial energy E naught will be a half times the capacitance times 3 squared, that is its initial energy. Then when it discharges, the energy E1, which is a half C times the new potential difference squared, is the same as 50% of the initial, is the same as 50% of E naught. So that means we shall have that a half CV squared, the new PD, V, is going to be equal to 50% is the same as 0.5 times E naught, which is a half, C times 3 squared. So C has cancelled, it is not necessary. And the half has cancelled, so we have that V squared is equal to half has cancelled. C has also cancelled. V squared is going to be 0.5 times 9. 0.5 times 9. Then it means V is going to be the square root of that. So V is going to be the square root of 4.5. Square root of 4.5, root of 4.5. So this is 2.1 volts. So that is the PD. State 2 functions of capacitors. State 2 functions of capacitors. We have said capacitors can be used to store energy. Store energy. That is one. Separate charges or separating charge. That is 2. Blocking direct current. Blocking DC. That is 3. We have seen smoothing. That is reducing the fluctuations in directional output voltage from the AC or from the rectified voltage. Timing circuits to produce time delays. Capacitors are used in timing circuits. That is 4 or that is 5. They are used in preventing sparks or preventing acing. Capacitors are used in tuning circuits of radios and TVs. Tuning circuits of radios and TVs. Capacitors are used in coupling, that is linking, joining one circuit to another. Coupling. They are used in producing electrical oscillations. You can't fail to state 2 out of all those ones. They can also be used as temporary power supplies. Temporary power supply. Temporary power supply. So you can't fail to state at least 2. You cannot fail to state only 2 out of all those ones. Okay, next. 3 uncharged capacitors of capacitance C1 and C2 and C3, C1, C2 and C3 are connected in series as shown here. A charge of positive Q is put on plate A. So on plate A, they have put positive Q. State and explain the charges that will be observed on the other plates of the capacitors. If we put positive Q there, automatically there will be negative Q here, positive Q here, negative Q there, positive Q there, negative Q there. So the charges that we are talking about are going to be negative Q, positive Q, negative Q, positive Q, negative Q. Reason? Charge must be conserved. By conservation of charge, by conservation of charge, by conservation of charge, or by charge conservation, by charge conservation, negative Q is induced on the opposite plate. Negative Q is induced on the opposite plate. So the charges will be, because they said you may draw on the figure, you can just add them in there. Like I have shown, when we have positive Q on one plate, it will be negative Q on the other plate. So by charge conservation, a charge negative Q is induced on the opposite plate. So the charges will be, are starting with the first one, that will be negative Q, positive Q, negative Q, positive Q, and negative Q in that order, because the first one has been stated. So the other charges will be those ones. Use your answer in Roman 1 to derive an expression for the combined capacitance of capacitors. Since they're in series, the charge is the same. So we know that the total PD, V will be the sum of the PDs across each, that is V1 plus V2 plus V3. And we know that Q is the same. The charge is the same. We also know that V is equal to Q over C. So we now substitute. So this will imply that where there is V, we have Q over C. This will be Q over C1 plus Q over C2 plus Q over C3, which therefore means that 1 over C is going to be 1 over C1 plus 1 over C2 plus 1 over C3. That's what we shall have as the total capacitance will be given by that expression. A capacitor of capacitance 12 microfarads is charged using a battery of EMF 9 volts as shown. Switch S1 is closed. So we have closed this one, and S2 is open. So in other words, the capacitor of 12 microfarads is being charged. The capacitor is now disconnected from the battery by opening S1. Calculate the energy stored. So let's find the energy stored. Of course, we know that energy is a half CV squared, or you can use a half QV, where you know that Q is CV. So this is going to be a half times the capacitance is 12, I guess. 12 times 10 power, because it is micro, it will be times 10 power negative 6 times the PD, which is 9.0 squared. So I press the calculator. So this is going to be 4.9 times 10 power negative 4 joules. Okay. The 12 microfarad capacitor is now connected to an uncharged capacitor of capacitance 20 microfarads by closing S. So they have opened S1 and they are now closing S2, so that this is going to share its energy, or to share its charge with the 20 microfarad capacitor. So let's see the question. The 12 microfarad capacitor is now connected to an uncharged capacitor of capacitance 20 microfarads by closing S2. Switch S1 remains open. The total energy stored in the two capacitors is now this. It is actually less than what we have calculated before. State why this value is different from your answer. We said every time the capacitor is charged, some of the energy is dissipated in the resistance of the wires. That's where the other amount of energy goes. Therefore, we are saying that the energy is dissipated. Energy is dissipated in the resistance. Energy is dissipated in the resistance of the wires as heat, or it can be dissipated as spark. Energy can be dissipated as a spark, or it is dissipated in the resistance of the wires. Energy is always dissipated in the resistance of the wires, or it is dissipated as a spark. The resistance of the wires as heat, or it is dissipated as a spark. That is that is the major reason as to why the energy stored when the capacitor discharges into another one is not the same as stored before. The potential difference between the plates is V. Here we have two plates, two parallel plates. The potential difference between the plates is V. The potential difference between the plates is V. The variation with the V of the magnitude of the charge Q on one plate is shown in the figure below. Okay, so they have showed us variation of Q, the variation of Q with the V on one plate. Okay, explain why the capacitor stores energy but not charge. We have explained this. The charges on the plates are equal and opposite. Resultant charge is 0. The charges on plates are equal. What is wrong with my pen? The charges on plates are equal and opposite. So the resultant charge is 0. So the capacitor does not store charge. But there is work done in separating the charges, which is the energy stored by the capacitor. The work done in separating the charges is the energy. Is the energy stored by the capacitor. Work done in separating the charges is the energy stored by the capacitor. Use the figure 3.2 to determine the capacitance of the capacitor. So we know that capacitance is charge over V. I can just use a single value since it is a straight line. And I can predict that it would go to the origin. So I will just use a simple value For charge, I may use, let me see, 1, 2, 3, 4, 5. Okay, you can use 10. Let me check 10. V, which is 10. V is 10. If I use V10, this is, I think that is 18. Okay, 18 millicolumns. I'll use 18. You can choose any value as long as they're easy to read. So 18 times 10 power negative 3 coulombs divided by V, which is 10. But we want the answer in microfarads. So this will be 1.8 times 10 power negative 3, again divided by 10 power negative 6, which is 1,800. Yes, 1,800 microfarads. Use the figure again to determine the loss in energy stored in the capacitor when the PD is reduced from 10 to 7.5. From 10 to 7.5, we have seen at 10, 7.5 is I think in the middle. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 7.5 should be around here, where the charge is this. The charge is that, but I may not need the charge anyway. I will use capacitance. So the energy, by the way, the energy can be the area under the graph. The energy can be equal to the area under the graph between 10.0 to 7.5, which is a trapezium. But it is easy to use a half CV squared. So this will be equal to a half. Capacitance is 1,800 times 10 power negative 6 as we calculated. Then times the difference in the PDs. So this will be 10.0 squared minus 7.5 squared. Do not first subtract before you square. That's wrong mathematics. So when I press my calculator, so this is giving me 39, or 3.9 times 10 power negative 2. 3.9 3.9 times 10 power negative 2. That is, when I move one step to the right, I think that is 39 millijoules. You can also find the area under the graph between these two parts. You can find the area under the graph between 10 and 7.5. So you can find the area under this part here to find the energy stored, the loss in energy stored in the capacitor. It will be approximately the same value. But substituting the formula is very easy. 3 capacitors X, Y, and Z, each of capacitance 10 microfarads, are connected as shown in the figure here. Initially, the capacitors are uncharged. Okay, a potential difference, I hope they are identical. A PD of 12 volts is applied between points A and B. So between A and B, the PD is 12 volts. Determine the magnitude of the charge on one plate of capacitor X. Determine the magnitude of charge on one plate of capacitor X. Okay. So if the capacitors are identical, let us assume the capacitors are identical. We know that the PD across the parallel combination is equal to half of the PD across a single capacitor. The PD across a parallel combination is equal to the PD across a single capacitor, but each capacitor has capacitance 10 microfarads. So we want the magnitude of the charge on one plate of the capacitor. We can find total capacitance. This is 10 plus 10, this is going to be 20 microfarads. 20 microfarads is now in series with another 10 microfarads. So total capacitance, so capacitance of Z and Y is 20 microfarads. So total capacitance is going to be product over sum. So that will be 20 times 10 over 20 plus 10, which gives us 20 or 200 over 30. I'll just write this as 20 over 3 as total capacitance. So all the charge appears on the plate of X because it is in series with the battery. All the charge appears. So I will find the charge, total charge is going to be total capacitance times total PD. Total capacitance is 20 over 3. Of course, it is in microfarads. I will not remove the micro because I need it again. Then times 12, and I think this is 4, that is 80 microcoulombs. So the total charge is 80 microcoulombs. Total charge is 80 microcoulombs. We can also use the concept of charge. Since total charge is the same, the charge on plate X is the same as total charge on ZY. And remember, charge is capacitance times V. So let's say the PD across X, let it be V. Then the PD across the parallel combination will be 12 minus V. So using the concepts of same charge, the charge across X will be capacitance, which is 10 times V. Then the charge across ZY will be total capacitance, which is 20 times 12 minus V. So I will now solve. Of course, 10, we have this side V is equal to 2 into 12 minus V. So we have that V is equal to 24 minus 2V. We now have that 3V is equal to 24 and V is equal to 8 volts. That means the PD across 10 microfarads is 8 volts. And note that X is inside the battery. We can even find the charge across it. So charge is going to be the PD, the capacitance, which is 10 times or 10 microfarads, or 10 times 10 power negative 6 times 8, which still gives us 80 microcoulombs using same charge. You can also use a simple relation. We know that in parallel, the capacitance is twice that in series, and yet capacitance is inversely proportional to PD. When the capacitance is twice, the PD is half of the other. So if we say PD across parallel is X, then PD across the one in series will be twice X. If we say the PD across the one in series is X, then the one in parallel will be a half of X. So that is mathematical relation. It may not be physics. If we say the PD across this one is X, then the PD across the other one is going to be a half of X. So that X plus a half of X, it is going to be 12. So this will give us X as still 8 volts. Now we can find the charge from charge is equal to C times V. It will give us the same thing. Define capacitance. So capacitance is the ratio of charge to potential difference. The ratio of charge to potential difference, that is capacitance. A capacitor is made of two metal plates. insulated from one another as shown in the figure. You can look at the figure. Okay. Explain why the capacitor stores energy but not charge. Stores energy but not charge. Remember, we have said the capacitor plates have equal magnitudes of positive and negative charges. Total charge on the capacitor is 0. But the charging process involves separating charges. The work done in separating the positive and negative charges is the energy stored by the capacitor. Therefore, we shall simply say capacitor plates have equal magnitudes of positive and negative charges. Equal magnitudes of positive and negative charges. So total charge or resultant charge on the capacitor is 0. It has the same number of positive charges as negative charges. So total charge on the capacitor plates, the total charge is 0. So does not store charge. But the charging process of a capacitor involves separating positive and negative charges. The charging process involves separating positive and negative charges. So the work done in separating the charges is the energy stored by the capacitor. So the work done in separating the charges is the energy stored by the capacitor. The work done in separating the charges is the energy stored by the capacitor. 3 uncharged capacitors X, Y, and Z each have capacitance 12 microfarads. They are connected as shown here. A potential difference of 9 volts is applied between points A and B. So between A and B, we have a battery of 9 volts. Calculate the combined capacitance of X, Y, and Z. So these two which are in parallel give us a total of 24. Just add them. Then they are now in series. So total capacitance X, capacitance Z, and Y is 24 microfarads. Now total capacitance, we now have 24 in series with the 12. That is going to be 12 times 24 over 12 plus 24. If you are still learning this, we just say 1 over C total is 1 over 12 plus 1 over 24. But if you have already learned it, just get product over sum when you have two capacitors. Pressing the calculator, from my calculator, this gives me 8.0 microfarads. 8.0, let me repeat, 12 times 24 divided by 20, 36, 8. So that is 8.0. Explain why when the potential difference of 9.0 volts is applied, the charge on one plate of capacitor X is 97 microcoulombs. Why is the charge on X 97 microcoulombs? You see that 97 X is in series with the battery. That means all the charge in the circuit must appear on the plate of X. So we can say since X is in series, all the charge appears on its plate. All the charge appears on its plate because it is in series. All the charge in the circuit appears on its plate. And we know that charge is equal to C times V. So this is going to be total capacitance, because all the charge I mean total charge. So total capacitance is 8 times 10 power negative 6, then times total PD which is 9. This is giving me 72 times 10 power negative 6 coulombs, which is 72 microcoulombs. So it means Q is 72 microcoulombs. And all this charge appears on the plates of X because it is in series. But this charge will be divided in the plates of Y and Z because they are in parallel. Okay, determine the PD across capacitor X. Now that we know the charge across it, the charge on each plate, and we know that we know the capacitance, then we know that PD is simply going to be the charge over capacitance. The charge is 72 times 10 power negative 6 divided by the capacitance, which is 12 microfarads, that is 12 times 10 power negative 6. And this is 12 by 12, 72 by 12, I think that is 6. So this is going to be 6.0. 6.0. Alternatively, you can also use the fact that the charge is the same. You can simply use the same charge. Concepts of same charge to solve the same part that we have solved. Same what? Same charge. Same charge Q. The charge on X is total charge on X should be equal to the total charge on YZ. That is total charge in the parallel combination. If the PD across X is V, then the PD across the parallel combination should be 9 minus V. So this means charge across X is going to be C, which is 12 times V. The charge across YZ, which is going to be total C, which is 24, times the PD, which is 9 minus V. So we have that V. Okay, we can reduce by 12, that is V. By 12, this will be 2 into 9 minus V. So this gives us V equals to 18 minus 2V. So 3V is equal to 18 and V is equal to 6 volts. That means the PD across 12 is still 6 volts. You can still use that formula to find the PD. So the answer here is 6 volts using two methods. You can choose one. Then again, determine the charge on one plate of the capacitor Y. Now the charge is going to divide because there are two capacitors. It is going to divide. The charge is going to be shared. However, you can look at the PD across Y equals to the PD across X. I mean total PD, which is 9 minus PD across X, which is 6. That is 3 volts. That is the PD across Y. Then the charge is going to be capacitance times V. The capacitance of Y is 12 times 10 power negative 6 times 3. And this gives us, I think, 36 microcoulombs. So this is 36 microcoulombs. Alternatively, you could just write a statement and say the charge is shared equally. The charge is shared equally. Remember the total charge which goes across, the total charge on X is going to be the total charge on Y and Z. This charge is going to be shared equally because these X and Y and Z are in parallel. So charge is shared equally. So the charge on Y is going to be 72 divided by 2, which is still 36 microcoulombs. State two functions of capacitors connected in electrical circuits. So the functions of capacitors are now part of us. Number one, you can talk about storing energy. Number two, you can talk about smoothing, that is making unidirectional voltage, output voltage, to be not to fluctuate. You can talk about separating charges, in the circuits. Separating charges, you can talk about blocking direct current. You can talk about timing circuits. Capacitors are used in timing circuits to control time. They are used to prevent sparks or prevent acing, to prevent sparks or to prevent acing. Capacitors are used in tuning circuits, tuning circuits, like for radios and TVs. Capacitors are used in coupling, that is joining one circuit onto another. Capacitors are used as temporary power supply. Capacitors are used in producing electrical oscillations. That is, all those are uses of capacitors. So producing electrical oscillations is how we come up with the tuning circuits. So together with the coil, the capacitor can be used to produce electrical oscillations, which are important during tuning. Three capacitors are connected in parallel to a power supply as shown here. The capacitors have capacitances C1, C2, and C3. The power supply provides a potential difference. We explain why the charge on the positive plate of each capacitor is different. In other words, why is the charge on each of these different? Not that they are in parallel. The PD across them is the same. And if the capacitance is different and V is the same, there is no way the charge will be the same because Q is equal to C times V. C is different, yet the PD is the same. And if C is different and the PD is the same, there is no way Q can be the same. Therefore, we can say the potential difference across each capacitor is the same. Potential difference across each capacitor is the same, and we know that charge is equal to C times V. Since capacitances are different, because the capacitances are different, it means Q is different. Because the capacitances are different, yet V is the same, then Q is going to be different. As simple as that. Okay. Use your answer in Roman 1 to show that the combined capacitance C of the three capacitors is given by that. So we know that capacitance C is charge over V. And we have seen that actually the charge is different. The charge is different, but total charge Q is going to be the sum of Q1, Q2, and Q3. So total charge Q is going to be equal to Q1 plus Q2 plus Q3. So this one implied that actually charge is equal to C times V. So we shall say C times V is equal to C1 times V plus C2 times V plus C3 times V, which when we factor out V cancels, C is going to be equal to C1 plus C2 plus C3. A student has available 3 capacitors, each of capacitance 12 microfarads. Draw circuit diagrams, one in each case, to show how the student connects the 3 capacitors to provide a combined capacitance of 8 microfarads. There are 3, so the 3 must be combined. Of course, you want 8. 8 is smaller than 12, so we need to think of connecting something in series to reduce total capacitance. But if I have 2 in parallel, that is 12 plus 12, which is 24. I know that 24 times 12 over 24 plus 12, that is 8. So I'll connect 2 in parallel and again in series with 1. You must add the connecting leads to show that there is power supply. So you can check if this is 12 microfarads and this is 12 microfarads. That one is 24 in parallel. This is 12 microfarads, so you check 12 times 24 over 12 plus 24. You notice that this is actually 8 microfarads. So it means my arrangement is correct. Then we have to get 18. I think 18 is 12 plus 6. How shall we have 6? We shall have 6 if we get 12 times 12 over 12 plus 12. I think that is 6. So in other words, we need 2 capacitors that are in series. They give us 6. And then we must add 6 to another capacitor which is of 12. So we must put it in parallel. So that is 2 in series, but again in parallel with 1. That will give us the total capacitance of 18. Okay, so those are the circuits that you would be drawing. An insulated metal sphere of radius r is situated in a vacuum. The charge Q on the sphere may be considered to be a point charge at the center. Write a formula in terms of R, Q, and V of the potential on the surface. That is a equation. V is equal to charge over 4 pi epsilon naught times R. Note that epsilon is permittivity of free space. Define capacitance. So we know that capacitance is the ratio of charge to potential. So capacitance is the ratio of charge to potential difference or to potential. And then that means capacitance is Q over V. So since V is Q over 4 pi epsilon naught, so this will be Q divided by Q over 4 pi epsilon naught times R. And this is going to give us, of course, Q will cancel, 4 pi goes up. That gives us 4 pi epsilon naught times R. So we have showed that capacitance is given by that several times. An isolated metal sphere has a radius 45 centimeters. Use the expression in A to calculate the capacitance in picofarads. So capacitance is going to be 4 pi epsilon naught times R. So this is 4 pi times epsilon is 8.85 times 10 power negative 12, permittivity of free space. R is 45 centimeters, that is 45 times 10 power negative 2. When I press my calculator, so from my calculator, I am getting a 50 picofarads. Let me check again. Okay, so this is 5.00 times 10 power negative 11, that is farads. When I divide by 10 power negative 12, so that is 5.00 times 10 power negative 11 divided by 10 power negative 12 to change it to picofarads. That is 50, or 50.0 if you want. The the sphere is charged to a potential of 9.0 volts. 9.0 times 10 power 5 volts. A spark occurs partially, discharging the sphere so that its potential is reduced to 3.6 times 10 power 5 volts. Determine the energy of the spark. Determine the energy of the spark. So we know that energy is going to be a half C V squared, or energy is a half QV, where you know that Q is C times V. So the energy of the spark is the difference in the energies. Energy of the spark is going to be equal to a half times capacitance, which is 50, times 10 power negative 12, times values of V. They were changing from 9 to 3, so that would be 9 times 10 power 5, that is squared, minus 3.6 times 10 power 5, this is also squared. These are multiplied by a half C. Pressing my calculator, so from my calculator, this is approximately 17. 3 capacitors, each of capacitance 48 microfarads, are connected as shown. So these ones are in series. Total is 48 plus 48, which is 96 microfarads. 96 is now in series with the 48. Calculate total capacitance. Now that we are experts, we shall just say total capacitance is product of a sum. That is 96 times 48 divided by 96 plus 48. When I press my calculator, this is giving me 32 microfarads. The maximum safe potential difference that can be applied across any one capacitor is 6 volts. That means the PD across one capacitor is 6 volts. Determine the maximum safe potential difference that can be applied between A and B. So if the PD across one capacitor is 6 volts, and that this can be the one in series, the PD across capacitors in parallel is going to be less than the PD across a capacitor in series. Because remember, capacitance is equal to charge over V. Capacitors in parallel will have a high value of capacitance, therefore they will have a smaller value of V. Now that the capacitors are identical, then we shall simply say that the PD across parallel combination the PD across parallel combination must be equal to a half the PD across a single capacitor. So if the PD across a parallel combination is V, then the PD across a single capacitor is going to be a half V. So in other words, the PD across a single capacitor is V. The PD across a parallel combination is going to be twice V. Therefore, we shall simply say, since for one capacitor it is 6, PD will be 6 plus a half times 6, because 6 is in series. Then in parallel it will be a half times 6, which gives us 9. So this will be 9.0 volts. That is the maximum PD. An uncharged capacitor is connected in series with a battery, a switch, and a resistor as shown here. The battery has 9 volts and negative internal resistance. The capacitor of the capacitance is 4700. The switch is closed at t equals to 0. During t equals to 0 to t equals to 4, the charge passing through the resistor is 22 millicoulombs. Calculate the energy transferred in the battery. Energy transferred in the battery is like energy supplied. So the energy transferred is going to be charge times the EMF, which is going to be the charge, that is 22 times 10 power negative 3 times the EMF, which is 9.0. And this gives us, from my calculator, yes, this is 0.20. Then determine for the capacitor at t equals 4 seconds, the PD across the capacitor. So capacitance is charge over V. We want PD. This means the PD is going to be charge over C. So the charge is 22 times 10 power negative 3 divided by the capacitance, which is 4700 microfarads times 10 power negative 6. Press my calculator. So this is 4.7 volts. The energy stored in the capacitor, the energy is equal to half CV squared. This is going to be equal to a half times capacitance, which is 4700 times 10 power negative 6 times the PD, which is 4.7 squared. Or you could also try to use energy is equal to a half QV. But this is giving me, let me check my calculator. From my calculator, this is 5.1 times 10 power negative 2 joules. I said you can also use energy is equal to a half QV. This will be a half times the charge is 22 times 10 power negative 3 times V, which is 4.7. I'm sure you'll get 5.1 times 10 power negative 2 joules. Suggest why your answer in A, Roman 1, and A, Roman 2 part 2 are different. In A Roman 1, we got 0.2 joules, and now we are getting 5.1 times 10 power negative 2. We know that energy is lost as thermal energy in the resistance of the wires. So energy is lost as thermal energy in the resistance of the wires. It can also be lost in the resistance of the battery It can also be lost since we have a resistor. It can be also lost as thermal energy in the resistor. So that makes the energy stored to be less than what we have seen before. Okay, so normally energy is lost as thermal energy either in the resistance of the wire, in the battery, or in the resistance of the resistor. Like in this case, they connected a resistor in the series with the capacitor. Okay, two flat metal plates are held a small distance apart by means of insulating pads, as shown here. Explain how the plates could act as capacitors. So to make these plates act as capacitors, we have to put a potential difference across them. In other words, maybe we shall connect them across a battery so that charges are now separate. Work is done in separating the charges. Therefore, we are saying a potential difference, a PD, is applied. A PD is applied. A PD is applied between the plates. A PD is applied between the plates, which causes charge separation. Which causes a charge separation between the plates. Thus, storing energy. Thus, storing energy as work done in separating the charges. So we must apply a PD between the plates. The PD is going to cause charge separation. As the charge separation work is done separating the charges, and the work done, remember, is the energy stored. That is how the plates will be used to act as a capacitor. So we have when the two-way switch is moved to position A, the capacitor is charged so that the potential difference across it is V. When the switch moves to position B, the capacitor is fully discharged through the sensitive ammeter. So we take it to A for charging, we take it to B for discharge. The switch moves repeatedly between A and B so that the capacitor charges and discharges with a frequency of F. That is the number of times it charges and discharges is F. So that the average current I in the ammeter is given by that. So we know that current is going to be charge over time. But we know that charge is going to be capacitance times V. We know also that the time is going to be 1 over the frequency, which means the frequency is 1 over the time it takes for charge and just for one charge and discharge. So we combine the two expressions. Current is therefore going to be, where there is Q, I put there CV, and over T, but remember 1 over T is F. So this is going to be CV times F, as simple as that. So what is very important is this expression here and this relationship here. Okay. For a PD V of 180 volts and a frequency F of switching of 50 Hertz, average current in the ammeter is 2.5 microamperes. Calculate the capacitance in picofarads. So since I has been got as CV times F, we want to find the capacitance. So capacitance C is going to be the current, which is 2.5 micro times 10 power negative 6 divided by V, which is 180 times the frequency, which is 50. Press our calculator. So this is giving me 2.78 times 10 power negative 10 in farads. So I'm now dividing this 2.78 times 10 power negative 10 divided by 10 power negative 12 to change it to pico. And this is giving me 280 farads, picofarads. I just rounded off to two significant figures. It is 280 picofarads, two significant figures. A second capacitor is connected into the circuit of the figure. The two capacitors are connected in parallel. Remember, when capacitors are in parallel, total capacitance is the sum, so it has a higher capacitance. Okay, state and explain the change, if any, in the average current in the ammeter. Change, if any, in the average current in the ammeter. So first of all, total capacitance increases. Total capacitance increases when we connect capacitors in parallel. So total capacitance increases, and since we have already seen from I equals to CVF, since I is directly proportional to C, then the average value of I increases. That's one way of looking at this. Alternatively, total capacitance increases, so it means from Q equals to CV, it means there is a greater charge. There is a greater charge because C has increased. The Q is directly proportional to C. So there is a greater charge. There is a greater charge. And if there is a greater charge, it means for each discharge, there will be a greater value of V, because I is going to be Q over T. From Q is equal to CV, since the capacitance is increased, there is a greater charge. So it means for each discharge, there's a greater charge, or no, let me say there's a greater charge for each discharge. There's a greater charge for each discharge, therefore there's a greater current. So we have a greater average current. So you can think about it in that way, that since we have the total capacitance increases, and from Q is equal to CV, it means there's a greater charge for each discharge. And since current is Q over T, it means there is a greater current. Alternatively, we can talk about total capacitance increases, and since from the expression we saw above, current is directly proportional to capacitance, average current increases. Define the capacitance of a parallel plate capacitor. This is the ratio. The ratio of charge on one of the plates to the potential difference. Across. to the potential difference across the plates. That is capacitance. State three functions of capacitors in electrical circuits. These are now many. You should now be familiar with them. Capacitors are used in smoothing. Capacitors are used for coupling. Capacitors are used in timing circuits. Capacitors are used to block DC, blocking DC. Capacitors are used in timing, I have talked about timing. Timing to produce time delays. By the way, when we talk about timing circuits, they are normally used to produce time delays. So they are used in tuning circuits, like for TVs and radios. They are used as temporary power supply. Temporary power supply. Capacitors are used for storing energy. They are used to prevent acing or to prevent sparks. To prevent sparks or to prevent acing. They are used to produce electrical oscillations or in oscillators to produce electrical oscillations. In other words, they are used in oscillators. You can't fail to state only three. You cannot fail. A student has available 4 capacitors, each of capacitance 24 microfarads. The capacitors are connected as shown in the figure. You notice that 3 are in series. The resultant is in parallel with 1. 3 are in series, if you are very observant. And these 3 capacitors are in series and they can form one capacitor, which is in parallel with the 24 microfarads. For the capacitors in series, we shall say 1 over total capacitance in series is going to be 1 over 24 plus 1 over 24 plus 1 over 24, which gives us 3 over 24. That is 1 over capacitance in series. 1 over capacitance in series. That means we get a reciprocal. So the capacitance in series is going to be 24 over 3, which is actually 8 microfarads. So in series we have 8. 8 microfarads is in parallel with 24. So we have now seen that 1 over capacitance in series is going to be 3 over 24, which meant that capacitance in series is 24 over 3, that is 8 microfarads. But 8 is in parallel with the 24 again, those ones we just add. So total capacitance is going to be 24 plus 8, which gives us 32 microfarads. So this is 32. A student has available only three capacitors, each of 12 microfarads. Draw diagrams, one in each case, to show how a student connects the capacitors to give a combined capacitance between the terminals of 18 microfarads. Remember, 18 is 12 plus 6. How shall I get, of course, 12 should be, capacitors giving you 12 microfarads should be in parallel with the one giving you 6. So you will get one capacitor, then you make it in parallel with the capacitors which give 6. These ones should be in series. Therefore, I'll just put here 2 capacitors in series. These ones I'm sure they will give me 6. And then they should be in parallel with the one which is of 12. So this is 12 microfarads 12 microfarads, 12 microfarads, and I think the total is 18. You can check. These ones which are in series, they give me 6 because that is 12 times 12 over 12 plus 12. I think those ones give me 144 over 24. 144 divided by 24, that is 6. Then plus 12, that is 18. Then these ones, this one is 18. I mean, this is 8 microfarads. 8 microfarads is the same as it is the same as 12. Then 12 must be reduced by one which is not necessarily 12. It should be 6 and 12 in series. Let me check. 12 times 6 over 12 plus 6. That is 12 times 6 divided by 18. That is 4. So how about if I say 12 plus 12, that is 24 times 12 divided by 24. I think that is 8, yes. So I'm going to have two capacitors in parallel. They will give me a total of 24. Two capacitors in parallel. They give me 24. So here I have 24 in parallel. Then I will need 24 times 12 over 24 times 12. So that means I must add another capacitor here in series. Okay, so this is going to be the circuit. This is 12 and this is 12. Those ones in parallel give me 24, but then in series with another one, that is 12, giving me a total of 8. So we just join this one there and we come up with such a circuit. Define capacitance of a parallel plate capacitor, that is the ratio of charge on one plate to the potential difference, to the PD, the potential difference across the plates. The ratio of the charge on one plate to the potential difference across the plates. That is a capacitance of a parallel plate capacitor. Okay, a student has 3 capacitors, 3, only 3. 2 have 4 microfarads and one has 8 microfarads. Draw a labeled circuit diagram, one in each case, to show how the 3 capacitors may be connected to give a total of 1.6. When 1.6 is smaller than each of these, that gives you an information that they should be in series. Try to begin by checking the 3 in series. If I connect 3 in series, can I get 1.6? Let's check. So we have 1, 2, 3. Let's say this is 8 microfarads. This is 4 microfarads and another 4 microfarads. I'll add the leads, the connecting leads. So we check. In series, 1 over total is 1 over 8 plus 1 over 4 plus 1 over 4. LCM is 8. 8 gives us 1 plus 2 plus 2, which gives us 5 over 8. 5 over 8? Yes. So we get now the reciprocal. C total is going to be 8 over 5. Let me check. 8 divided by 5 is 1.6. So this is correct. the 3 should be in series. This is just checking if the combination gives you total. Remember, there is no specific formula, so you just check. Just draw, think of a circuits, you draw and then check the combination. But of course, the value given is a guide. If the value is smaller, then think of capacitors in series. If a value is very large, then think of capacitors in parallel. For example, we have 10 microfarads, it is greater than n of the 2. That means there should be some parallel combination. But you notice that when I join the 4 microfarads in series, the 4 microfarads, both of them in series, they will give me 4 times 4 over 4 plus 4, which is 16 over 8, which is 2. And when I add 2 to 8, I will get 10. So 10 is 2 plus 8. 8, that means capacitors of giving 2 microfarads should be in series, in parallel with capacitors of giving 8 microfarads. This will be equivalent to having 2 capacitors in series of 4 microfarads. So this is 4, that is 4, but in parallel with the capacitor of 8 microfarads. That is 8 microfarads. Do not forget to add the connecting leads. Remember, it is just 1 mark. When you lose it, you have lost something big. So the 4 microfarad capacitors in series gives us 2. Then we combine it in parallel with the 8 microfarad capacitor. A capacitor C of capacitance 47 microfarads is connected across the output terminals of a bridge rectifier as shown here. Okay. So a bridge rectifier produces full wave rectification. When we add a capacitor, we are doing what we call smoothing. So we have the graph there. Use data from the figure to determine the energy transfer from the capacitor C to the resistor R between T1 here up to T2 here. We want the energy transfer. I want you to note that discharge is occurring, I think it is within this peak, and I think this is 7.0 because the scale here is 0.2 divided by 2 divided by 5, that is 0.4, so this is 7.0. So the discharge occurs from 7.0 up to this level here, up to 4. So we can say discharge, because there are 3 marks. We shall start by simple explanation. Discharge occurs from 7.0 volts to 4.0 volts. That's how discharge occurs. So we want the energy transferred from the capacitor to the resistor. So the energy is going to be a half CV squared. So this is going to be a half times the capacitor. They gave us a capacitance of 47 microfarads. So the capacitance is 47 times 10 power negative 6. I think it is micro. 47. So 47 times 10 power negative 6 times now added, because this charge occurs from 7 volts to 4 volts, that will be equivalent to the energy which is given out. So this will be 7.0 squared minus 4.0 squared. We get the difference in the energy from my calculator. So from the calculator, this is actually 7.8 times 10 power negative 4 joules. So this is 7.8 times 10 power negative 4. That is the energy which is transferred from the capacitor to the resistor. Because from T1 that is discharge, from T2 that is charging. Okay. State two different functions of capacitors in electrical circuits. We have now mentioned these ones. Talk about storing energy. Capacitor stores energy. Talk about smoothing. Capacitors are used in smoothing. Talk about blocking direct current. Capacitors are used to block DC. Talk about timing or producing time delays. You can talk about coupling. Capacitors are used in coupling. You can talk about temporary power supply. You can talk about tuning circuits. You can talk about producing oscillations in circuits, producing electrical oscillations. You can talk about preventing sparks. So all those ones are separating charges. You can also add separating charges, not storing charge, but separating charge. All those are some of the applications or functions of capacitors. Three uncharged capacitors C1, C2, and C3 are connected in series with a battery by an electromotive force E under a switch as shown here. Three uncharged capacitors, this was a repetition, sorry. When the switch is closed, there is a charge positive Q on one plate of the capacitor of C1. So there is a charge positive Q this side. So that means there will be negative Q there, positive Q there. So show that the combined capacitance is that. Because they're in series, the charge is the same. So the charge is the same, Q. The charge is the same, but the EMF of the battery is going to be the PD across the first capacitor plus the PD across the second one plus the PD across the third one. And the EMF of the battery will be total charge over total capacitance. That is the EMF of the battery. The PD across each is going to be charge over the capacitance across each. So we shall say Q over C is going to be Q over C1 plus Q over C2 plus Q over C3, which when we factor out Q, 1 over C1 plus 1 over C2, Q cancels out. Hence, we conclude that 1 over C is equal to 1 over C1 plus 1 over C2 plus 1 over C3. That is the total capacitance. Okay. The student has available 4 capacitors, only 4, each of 20 microfarads. Draw circuit diagrams, one in each case, to show how the student may connect some or all. So it's not mandatory to have all. Some or all the capacitors to produce a combined capacitance of 60. I think 60 is easy. When you combine the 3 in parallel, you just sum up to reach 60. So the easiest is having the three in parallel. So we have 1, 2, 3 in parallel. Do not forget the connecting leads. That one gives us automatically 60. because each of these is 20, 20, we just add. That gives us 60. Make sure that the plates are equal in length. Otherwise, they may look like battery terminals. They may look like battery terminals. So that one is 1. Then we have 15. Note that 15 is less than even 1 capacitor. So you think about connection in series. But I want you to note that 60, if you're a good mathematician, you will notice that 60 times 20 over 60 plus 20 is going to be the same as 1200 over 80. And 120 divided by 8 is actually 15. Therefore, many times the second part always, there is a way it relates to the first part. So you begin by checking, can I combine the first part with another resistor? So that means we shall have the 3 parallel combination, which gives us 60. And on it we shall add 1 in series. So now we have 60 in parallel times 20 in series over 60 plus 20, which gives us 15. So this will be our arrangement. As simple as that. Okay. Explain what is meant by the capacitance of a parallel plate capacitor. This one is the ratio of charge on one plate to the potential difference between the two plates. The ratio of the charge on one plate to the potential difference between the two plates. That is the capacitance of a parallel plate capacitor. A parallel plate capacitor C is connected into the circuit as shown here. So look at the circuit. We can turn the switch to X, the capacitor charges. We turn the switch to the Y, and the capacitor, there's a reading in the ammeter. When the switch S is at position X, the battery of the EMF 120 and negligible internal resistance is connected to capacitor C. When switch S is at position Y, the capacitor C is discharged through the sensitive ammeter. The switch vibrates so that it is first in position X, then moves to position Y, then back to position X 50 times each second. So this is going to be frequency. The current recorded on the ammeter is 4.5 microamperes. Determine the charge in coulomb passing through the ammeter in 1.0 seconds. Charge. Of course, we know that charge is going to be I times T, current times time. And the charge is going to be the current, which is 4.5 times 10 power negative 6, that is micro. Then times time, which is 1.0 seconds. And I think this is going to be 4.5 times 10 power negative 6 coulombs. Okay. Then determine the charge on one plate of the capacitor each time that it is discharged. The charge on one plate of the capacitor each time that it is charged. So first of all, we need the time for charging. Time is going to be equal to 1 over frequency, that is the period for charging. It's 1 over the frequency, which is 1 over 50. So time for charging is 0.02 seconds. And remember, the charge passing each second is that. And yet the time for charging is 0.02 seconds. Therefore, the charge on one plate Q on one plate is going to be 0.02 seconds times 4.5 times 10 power negative 6. And when I press my calculator, I think that is 9. That is 9.0 times 10 power negative 8 coulombs. Then the capacitance, determine the capacitance of capacitor C. We have now to determine the capacitance. We have found the charge. The PD is, when it is fully charged, it is going to be 120. Now we can find the capacitance. So the capacitance C is going to be charge over V, which charge is 9.0 times 10 power negative 8 divided by V, which is 120. So from my calculator, this gives me 7.5 times 10 power negative 10 farads. Okay. A second capacitor having a capacitance equal to that of capacitor C is now placed in series. When we have capacitors in series, total capacitance reduces. If they are identical and they are in series, total capacitance is halved. So they are saying it is having the same capacitance as the one we had before. That means total capacitance becomes half of half of the one we had before, because in series, total capacitance is a product of a sum. So I just explain the effect of the current recorded on the ammeter. So we are saying total capacitance is halved. Total capacitance is halved. Total capacitance becomes half or is halved. Remember, charge is equal to C times V. If charge is C times V, so charge is also halved. Charge is also halved. And if charge is halved, remember current is charge over time, it means the current is halved. So the current is halved. Remember, current is charge over time. Total capacitance is halved when we have capacitors in series. If they are identical, it is halved. And if Q is CV, so the charge is also halved. So the current is halved because the capacitor, as a result of having a second capacitor in series with the first one. Okay. Lastly, on the last question, explain what is meant by the capacitance of a parallel plate capacitor. Still, we now know that this is the ratio of the charge on one plate to the potential difference, to the PD, the potential difference between the two plates. The ratio of the charge on one plate to the potential difference between the two plates, that is the capacitance. Three parallel plate capacitors, each of capacitance is 6 microfarads. Draw circuit diagrams, one in each case, to show how the capacitors may be connected together to give a combined capacitance. There are only 3. We want 9. So now that means two capacitors should give us 3 microfarads. Remember, 9 is 3 plus 6. Therefore, we need 3, and we connect it in parallel with one which is 6 microfarads. So to get 3, we need 2 in series, I think. Let's check. 6 times 6 over 6 times 6. That is 36. 6 plus 6. 36 over 12. I think that is 3. So we shall have 2 capacitors in series. Those ones will give us 3 microfarads in total, connected in parallel with another one and we shall just add the connecting leads. Then 4 microfarads. 4. Suppose we relate it to the first one. If we have 2 in parallel, 6 plus 6 will give us 12. So 12 times 6 over 12 plus 6, that is going to give us 12, that is 72 over 18, that is 4. So we shall have 2 in parallel, 2 capacitors in parallel, those ones will give us 12. But then we need to combine them with 1 of 6 in series, so that we have 12 times 6 over 12 plus 6 to be able to get 4. So this will be our circuit. Do not forget the connecting leads. But see, 2 capacitors of capacitance, 3 microfarads, 2 microfarads are connected in series with a battery of EMF 8 as shown here. Of course, they're in series. Combined capacitance, I will just say product over sum. Or if you want, 1 over C total is going to be 1 over 3 plus 1 over 2. So C total is going to be 3 times 2 over 3 plus 2. 3 times 2 over 3 plus 2, which is going to be 6 over 5. And I think that is 1.2. So the total capacitance is 1.2 microfarads. Use your answer in Roman 1, that is total capacitance, to determine for the capacitor of capacitance 3 microfarads the charge. So we know that charge is equal to C times V. All the charge in the capacitor is going to be on the plate. So this can be total charge, which is total capacitance times total PD. So this will be 1.2 times PD, which is 8. And this is giving me, that I think that is 9.6. So this is going to be 9.6. That is 9.6. Then the energy stored in the capacitor. Energy is of course half QV, but we know that Q is equal to C times V. So energy can also be a half CV squared, and then so you can use a half CV squared, but of course you could also substitute and say, okay, we know that V is Q over C. So energy can also be a half Q squared divided by C. Let's check which one is easy to use. We have the charge and we have the capacitance as 3 microfarads. So I will use the last one. So the energy stored is going to be a half times the charge, which is 9.6. Since we want it in joules, so it will be times 10 power negative 6. This should be squared divided by the capacitance, which is 3 times 10 power negative 3, or 3.0 times 10 power negative 3. 3.0 times 10 power negative 3. Is it negative 3? No, negative 6. Okay. So I press my calculator. You could first substitute in Q and V. You could substitute in QV, or you first find the Q from, but Q is already found, charge is already there. All you needed is maybe, anyway, just substitute in one of those equations. Whichever you substitute in will give you a correct value. You could use CV squared if you know V is given, or you would be able to find the V across 2 microfarads. You can't use V as 8, that would be wrong. You cannot use V as 8, that would be wrong. That's why I labor to go and find, because I know Q is for that plate, and I know I can use the capacitance of that same capacitor. So from my calculator, Okay, so from my calculator, I am getting 1.5 times 10 power negative 5 joules. So that marks the end of capacitance. I know you will be thinking that the next unit should be oscillations. I know some of you are waiting for oscillations so much because the carries much marks. But like I told you, I follow my classes. I have two classes which are sitting May, June, and we had our next chapter in one of the classes is medical physics. Past paper questions for medical physics, because in one of the classes we covered oscillations, we covered quantum physics, we covered astrophysics, and but I'm going to record this at the end of this month of November. I'll record the oscillations too. I will record the quantum physics too because they are very ready for recording. Thank you for watching this video and I hope you have enjoyed it. See you in medical physics. Bye bye.